Scenario: a modified Atwood machine has one hanging mass and one on a surface with friction. Here I labeled the diagram for you so you can see it. Here's the question. You want to describe the direction of the center of mass when the hanging mass is let go. Here's the answer. Well, it's going to go downwards and to the right. Likewise, it is essentially going clockwise like that because the hanging mass is going to pull it down. You want to write the equation for the acceleration of the center of mass. So the summation of all the forces of this system is the force of, oh, this is without friction. So this is without friction so far. So this goes away. All right. So the only force here is the force of gravity on block 1. Okay. The mass of the system is m1 plus m2. So to solve for it, we divide by that. So the acceleration of the system is defined by the force of gravity on the hanging block, m1. So it's m1 times g divided by the system's mass, m1 plus m2. Now the table has friction right there. That's the friction part. You want to write the new equation. Don't ever start from scratch. Just reuse it. So reuse this one. Okay? Reuse it. There is just a new part that comes here. This is now going to be the force of friction in it. Okay? The force of friction that I add here is mu mg2 because here the force going down is m2g. Force normal is m2g. So force of friction, which is mu Fn, force normal, becomes m2g. That's how it's mu m2g. So this would be the acceleration for this situation. Okay? Notice, it's the same thing as before. All we did was minus mu m2g, which is the force of friction. The last question. Given that the table has friction now, when the hanging mass is let go, the system remains at rest. Explain why the system doesn't move. The system won't move if friction is greater. So the force of gravity isn't strong enough to overcome the static friction on block 2. So mu m2g is greater than the gravity pulling down m1g. Okay, this explains why the system remains at rest. There you go.